having me. It's great to be here. So I will talk about my work on hierarchical dense subgraph discovery. It's like a collection of works that I have performed in the last few years. So I will try to give some kind of perspective on what are the models, algorithms, and why do we do this and all, and what kind of applications are useful. So the problem that we're interested in is the dense subgraph discovery. I think I don't need to motivate you about the graphs, and this must be the last audience for that. So you're interested basically in the measure of connectedness on edges, and by this I have a very simple metric. It's just the edge density, number of edge over all the possible, and it's just between 0 and 1. It's 1 for a click, and we are always looking for as large as possible click-like structures. And one of the interesting things about real-world networks is they are globally sparse, so the number of edges is way less than the number of vertex square. But if you check the immediate neighborhood of a vertex or an edge, you'll find dense structures. So this is also known as the high clustering coefficient, and it basically gives us an opportunity to find dense regions in a local way. So our aim is basically finding many non-trivial size subgraphs with high density, and we also want to put some kind of relationships among them. So we want to create some kind of a spectrum of the density and size. So dense subgraphs with smaller sizes and the less basically dense subgraphs with larger sizes, and some relationships among those. And it sounds very similar to the classical graph clustering or the common detection problem, but the main subtle difference is here we are just looking for the absolute density. So I'm just interested inside of the graph. I'm not looking for the sparse cut, which is most often the harder problem. So the relative density is basically looking at the sparse cuts ratio versus the inner density, and that's what they use in the graph clustering. But here we are just interested in dense regions. That's all. And why do those dense subgraphs matter? I think in any real-world network, if you find some dense regions, it will give you some interesting information that you cannot find anywhere in the graph. So in general, I classify those as some significance or anomaly kind of applications. And there's also like it has been used for computation itself and summarization of data. A very famous example is the spending farms. So in the early stages of web search engine development, so people figured out that there are so many spam links, and they are basically linking to each other, creating huge clicks. And if you can filter those out, the performance of your search engine will drastically improve. So that was like one of the early examples of why those dense or large click, quasi-click kind of structures matter. Another interesting thing in more real-time data is people have been using the Twitter stream to basically extract entities and putting very simple relationships among them based on the co-occurrences, and they just generate some automatic news stories. So when Bin Laden was killed in Abu Dhabi, most of the tweets were mentioning Abu Dhabi, Bin Laden, Obama, CIA, and by just watching those for a limited time, you can create certain very small graphs, and you can model those as the dense subgraphs to create some news stories. Another interesting kind of application domain to me is the computation itself. So online social networking is kind of one of the big things that drives our research actually. And in this work, Gionis et al. Observed that if you want to improve the system throughput in a distributed cluster kind of environment where you run an online social network, then you can actually you can leverage the friendships among people to improve your system throughput. It basically translates to you handle the requests of two friends by basically finding a third common friend and just using the materialization of that third friend. And at the end, it is basically finding dense subgraphs in those online social network, and the optimize your system accordingly. And another, I think one of the very important things in overall data science is being able to visualize your data, at least to make some sense. And then subgraphs have been historically used for that. You basically find dense subgraphs and you put on the center, so those are red regions, and then so that this basically reflects core periphery structure as well. And then you put the peripheral nodes on the outside, and the dense subgraph discovery is kind of a fundamental building block for this purpose. So in our work, we basically focused on two models, pretty popular recently. One is k-core and the other is k-truss. So they both find dense subgraphs with hierarchical relationships. So k-core is a very useful thing for a diverse range of applications. I think the introduction of this concept explains everything. It was co-introduced by different people in 1983. So one of these venues was the Social Networks Journal, and the other was the Science Conference on some applied math. So k-core was used for improving graph coloring, basically, and also for finding some kind of good seed beds for social communities. And the definitions are pretty simple. The only thing we are looking for is in a k-core, every vertex should have at least k edges, and that should be the maximal thing. And in that case, this toy graph has the entire thing is a two-core. I basically check the vertex with the minimum degree, and the blue region is three-core because the minimum degree in that blue region is at this one or this one. I mean, we are just looking at in the degree inside the graph. So, and the nice thing is those different k-cores for different k values create some kind of hierarchy. So they are nested. Two-core includes three-core. So on a related kind of approach, it has been introduced that k-truss been introduced to work on a higher order. So the idea was basically, what if you work on edges and triangles instead of vertices and degrees? So definitions are pretty much like the same, except you replace a word. Every edge should have at least k triangles. So I am asking for every edge in that subgraph to participate in that k triangles. And algorithm-wise, and all the kind of optimizations that you can apply for k-core, you can go and do the same for the k-truss. For the same thing, for instance, the toy graph, we find that the entire thing is zero truss because that edge has no triangle, but we find more detailed structure inside. So this black part is one truss, that edge has one triangle only, and we are looking for that least thing. And we find two trusses, one that forklift and the other that structure. And again, we find some kind of nested relationships. So zero truss includes two truss, one truss, and there is another two truss inside one truss. So I'm able to basically construct some kind of relationships among the subgraphs with varying densities and sizes. And I will show more on that, but in those hierarchies, the density metric that we define is always increasing when you go to the bottom side. And of course, those are the containment relationships. So this is always larger than this. And of course, there might be some vertices in this graph, in this part, which do not exist in this. So this vertex is here but not here. And we don't show it as like another kind of leaf child. So why do we choose those k-truss decompositions things? There are like multiple benefits. The very first thing that we use basically is those current truss decompositions actually give you some indices on vertices and edges. So if you want to do some kind of a query-driven algorithm or application, you just look at a vertex and you will have some value that indicates the density around that vertex. Or in the truss case, it's an edge. So every edge has some value, and it will tell you about how dense the structured amount of around that vertex or edge. And historically, the core decomposition and also truss decomposition have been used to find the influential spreaders So this is something very interesting and a very simple way to tell the difference between different types of the star vertices. So hops are not always influential. If you have a high degree, it doesn't mean that you will be influential at all. And the very simple example from Maxim Kitsak's paper is that blue and the yellow vertices have the same degree, but the thing is, yellow is connected to all the low degree vertices, so its influence is limited, but the blue vertex is connected to other high degree vertices, and that is where the impact is coming. And the k-core exactly tells you the difference between the blue and the yellow thing. It's like a 3 versus 1 for numbers. So it basically helps us to focus on that isolated star problem. And I mentioned that before regarding the seed beds, so you can use those k-truss decompositions to filter out or to accelerate many harder problems. If you want to find the maximal click, or let's say if you want to find the densest subgraph, which has a different method, you try to optimize the average degree over all the graph. And the algorithm that solves this problem has a super quadratic complexity, and it basically makes use of a maximum flow computation, which you can't really do on a large scale network. But just applying that core decomposition will give you 2 approximation, which is way better in practice, and the complexity is just linear. And similarly, maximal click finding, you can basically use k-truss decompositions to filter out your search space and they focus on a very smaller subgraph to find your maximum clicks. So the algorithm-wise, both algorithms has a methodology that solves, which is known as a peeling. So you can consider that you start peeling and orange or onion from the outside to the inside. And what you do is you assign the density indicators on each vertex in the k-core case. So the algorithm is pretty simple. You start from the degrees, and at each step, find the minimum degree vertex, adjust the neighbor degrees, and then assign the core number. So 2 becomes the minimum degree vertex here. I assign the core number and decrement the degrees of the neighbors. And I just continue until I have all the core numbers. And at the end, the k-core subgraphs basically can be defined by a simple BFS traversal on those core numbers. So you basically have the indices, and you let the user to find whatever k-core she's looking for. And the complexity-wise, this is the thing that I just told you, the linear complexity. You just do OE work, and in practice you can do really good improvements by using the buckets data structures that you use in bucket sort, because degrees have a limited range, and you don't need to. You don't need to sort everything at each time to find the minimum. And for the trusses, we have a very similar thing, which goes on the edges and triangle counts, and its complexity is proportional to the sum of degree squares.
So for the edges, so here, right, I just looked at degree, which is something which is very simple. For the edges, I need to count the number of triangles,
right,
which is harder.
Yeah, you should have like a trip. The first step is to compute the triangle count of all the edges. So this is like, this includes inter-truss computation.
I see. And then, so then when but then I have to do that repeatedly as I get the triangles out, or no?
There are like multiple things that you can do. Most of them we can't afford to store triangles, but we can store the triangle counts.
I see.
So, and at each time in that peeling process, you can just go find your neighbor edges and adjust the triangle counts.
I see.
But I mean, most of the time it is not feasible to store the triangles itself. Just counts are fine. So, I told you all this about the previous works, that k-core and k-truss are different things and so on and so forth. So what I did, what we observed is basically start with this. We basically saw that the k-truss is actually just a k-core if you basically consider like a correct graph model. So if you think about a bipartite graph or a hypergraph, where you have edges on one side and triangles on the other side, and doing k-core decomposition basically gives you the same thing, and in this case it becomes a truss decomposition. So you basically build a bipartite graph, and those are not a binary relationship, so you need to tweak the neighborhood definitions. But at the end, again, you start from the minimum degree thing, adjust the neighbors at each step, and the rest of the algorithm is the same. That was my main kind of observation. And the natural question to ask was, why do we limit ourselves to triangles? So you can just go beyond. I mean, theoretically, you can say vertex at 1 click, edge at 2 click, and triangles at 3 click. And this first one is the k-core, the second one is k-truss, and we said, okay, let's just go for R and S triangles. And of course, we are looking for R is less than S, and looking for the involvement of R clicks in S clicks. Again, the model is saying, whatever graph you have, you put your R clicks on the left side, R clicks on the S clicks on the right side, and you basically connect if that R click is a part of that S click. So
yeah, but this requires you to get the triangles, right?
This requires you to
Yeah.
I mean,
Right.
There's three.
Not just the count.
Yeah, right.
Right.
So this basically is a hypergraph, a uniform hypergraph where you have the same degree for all the hyperedges. So it's always S choose R. In this case, it's 4. And algorithmically, you can apply the same peeling procedures on this bipartite graph or this hypergraph, let's say, and again get some density indicators on triangles this time. So accordingly, we define a nucleus decomposition thing, which is basically saying every R click takes part in at least k number of S clicks, and then there is also an additional kind of criteria which can create a huge difference in the subgraph. So we are looking for the R click connections. We ask each R click in that subgraph is connected by a series of S clicks. So in the vertex and degree case, it's trivial, regular connectivity, but in the tree case, it's something different. So it basically generalizes k-core and k-truss for different R and S values. And regarding that connectivity thing in the k-truss, we say that A and C are not connected in the context of k-truss because we cannot reach from A to C by a series of triangles, but A and B are triangle connected because it's basically known as a triangle connectivity in some other works, but you can go from A to B by a series of triangles.
Sorry, I missed it. What's the difference between an R click and an S click?
So R click is basically, those are just parameters of the algorithm. R is less than S all the time.
I see.
Yeah. R click is a subgraph with R vertices complete graph.
I see.
And we also explored what different R and S values are corresponding to. For instance, here, 2, 3, and 2, 4 have like a different benefits. So 2, 3 is each edge has at least 2 triangles, and in that case, each edge has at least 2 4 clicks, and for the same number of nodes, we find denser structure there. So there's like definitely density is proportional to the S, R values, and in that case, R is the constant, and the larger the denser the graph is. And as I said, the peeling procedures just works as we described. You create an R clicks and S clicks, and you do your degree-based procedures. You start from here to find the minimum degree vertex and adjust the neighbor degrees at each step. And overall, it is an expensive thing. And for 3, 4, for instance, the complexity is proportional to the summation of clustering coefficients times the degree cube of each vertex, which is like a huge thing. You can't afford that normally. But it turns out that it fits very well with some kind of a properties of the real-world networks, where the clustering coefficients decay with degree. So if you have a large degree, the clustering coefficient is likely to be very low, and that's where we have our algorithm practical. We can always come up with some corner case, but for many real-world networks, we can leverage those characteristics, and this entire 3-4 computation can be scaled to tens of millions of edges in a few minutes for in a sequential basis. I will talk about some other algorithmic improvements later. So, of course, we tested and we saw what those subgraphs are corresponding to. And these colorful visualizations are corresponding to the nested hierarchies. In this case, I just took that Facebook network with 4,000 nodes and the 88,000 edges. And I just show all the subgraphs, which I call nucleus, with at least 10 vertices. And each subgraph is color-coded for the density in 0 and 1.
What do the edges mean? That's a lot of edges for that many vertices. Do you remember?
You mean this?
Yeah. So I imagine that each vertex is like a person's account. But
yes,
what are the 88,000? That's a lot of edges.
Those are friendship relations.
Excuse me?
Friendship relationships.
Friendship relationships.
So each,
I see.
it's a Facebook. I think it's one of those Facebook 100 data sets.
I see.
So each person is a person, each not a person, and the edge is the friendship.
I see.
Average degrees are 22. So we basically constructed different hierarchies for our different RNS values, and we find nothing interesting in the K-code at all. So if you have that kind of a hierarchy, the first thing that you look for is the different leaves, right? The bottom subgraphs, where you can create the most diversity. You won't have like a similar structure, because we know there's like containment relations. This contains this, and we want to find as many subgraphs as possible with larger density and a diverse kind of set of vertices. But if you go to just 2 tree, you definitely have like a more branching, more relationships in terms of the root subgraph is always the entire graph, and in 2-3 case you have many red circles. In this case, those are between 10 and 100 vertices. And even when you go for a 3-4, you have even better structure. So this is like a part of that tree actually, and you have more connected components at the top level, which is corresponding to each of these kids on the second level.
I'm sorry, what does the 3-4 again mean here?
So 3-4 basically means every triangle has at least k forklifts.
I see. Every triangle I see has at least k 4 pleats.
Yeah.
Okay.
So every edge has k triangles, and every vertex has k edges.
I see.
So overall, this comparison of the hierarchies give us hope in terms of what 3-4 can offer to us on top of 2-3, and definitely for 1-2 K-4 decomposition. So another thing we checked was what exactly, in the previous graph, we don't know what each node corresponds to. We have no metadata, but here we basically explored the American Physics Journal Citation first. So those are the papers in Physical Review A, B. I think it's pretty popular among physicists and even network scientists. I remember reading a lot of papers from those journals. So what I did is just look for 2 seminal papers in the network science, and they took the subgraph that contains those 2 papers and having the largest size. Having the smallest size. So on the left, I have 2-3 nuclei, parts of the nuclei basically for these 2 seminal papers, and the smallest subgraph that contains those 2, and this is the 3-4 nuclei. And the graphs that I basically obtained are corresponding to the papers on the same subjects. So, for instance, those 10 papers which are just citing each other in the timeline, creating a click, are all about the percolation theory. And I can find more details on the 3-4 side. For instance, I can find those 25 synchronization networks which are lost in this big subgraph in the 2-3 case, or there are like 19 papers on random walls, and also there are like 13 papers on epidemic spreading, which are again get lost in some larger green subgraphs in the 2-3 nuclei. So, are there any questions so far? So one thing that we always thought is the unipartite graphs. Most of the graphs have the pairwise relations between all the possible entities. But if you think about different types of the graphs, for instance, the bipartite graphs, it's a completely different picture. So in the bipartite realm, those are the relationships between orders and papers. So multiple order writes a paper. Or you have word document relationships. The document has so many words in it. Or which actors are acting in a given movie. This kind of a similar relationship. So all of those relations are bipartite in nature. There's no triangle by definition. And a very common kind of practice to deal with that kind of data is a projection. So you basically convert this to a unipartite version by using the order-paper relationships to create the co-authorship graph. So everyone is author, and there's an edge between two if they publish the paper together. And they're even like a weighted kind of variance for that projection. But one very important thing, if you got scale, is the number of edges just explodes in that case. And the reason is, for every paper with D orders, you create a D click in the graph. And that cannot be affordable in large scale. We observe like up to 100 times increase in the number of edges. This is the raw bipartite graph, and this is the projection. It can definitely increase from 500,000 to 44 million easily. And the other thing is you lose information, and even in the weighted model. So it's a very simple thing. If there are like 3 authors publishing papers in different papers together, you can basically find kind of 2 different bipartite graphs that project the same thing. So in this case, there is no paper that is published by 3 researchers, but they still form a triangle, and in that case, 2 papers where they all involved, but still the triangle. And that information loss is still weighted for the weighted projection. And our idea was, why don't we just, focus on the bipartite network directly and define some kind of triangle-like subgraphs to apply those truss, core, and the nucleus kind of decompositions. And the related question, of course, is what is a triangle in the bipartite realm? So, triangle is a very important thing. This is like the smallest, not trivial thing that you can consider above nodes and edges. And there are basically previous studies on that, but how do you define the smallest meaningful structures in a bipartite graph? And the one we choose is like a 2 biclick, which is called as butterfly thanks to Ali's kids. So the idea is basically you want 2 nodes from each side, and you want them all connected. And once you have that butterfly definition, you can go and define very similar things as within the nucleus decomposition. So you can define something called k-tip, which is each vertex participates in at least k butterflies, or the k-wing is each edge participates in k butterflies. And this gives like again, comparison of those 2 concepts. Wing will give you more details, denser subgraphs with, of course, an additional cost of computation. And the algorithm-wise, you can use the peeling. In that case, you need to construct the hypergraph of that bipartite graph, where you have nodes on one side and the butterflies on the other side. For the not butterfly, vertex butterfly, sorry. For the edge butterfly, it will be the edges and butterflies. And as I said, the bipartite graphs are like prevalent, and there are real-world networks that are like bipartite in nature. And two of those that we focused on with metadata has the Amazon's Kindle data sets. So those are the products and users who rates those products. We just take the undirected, simple bipartite graph. We even ignore the rating data and the temporal information. And when I do that analysis, one of the interesting subgraphs in the tree hierarchy was 38 books on self-improvement kind of topics. And there were 3 subgraphs on it. 6 of them are basically on relationship guidance, how to find a spouse kind of books. 20 on the healthy lifestyle, so how to make a good diet or do some kind of yoga exercises. And the most interesting part was in the last, where we find 10 books on stocks, like personal finance kind of things, and dogs. So this is basically the graph corresponding to that 10 books. We have 4 users, and those are the personal finance books, where you have to make money at home, or finding some kind of a good keywords to be used in marketing kind of things. And there are 4 books here. This is the elementary level linear algebra book. Those 2 are dog training, and this is something about how to get rid of trash at home. So when we check the actual data, what are the ratings on those edges and what are the temporal information, there's a striking thing. So as you can imagine, all of those ratings are 5 stars, and the temporal relationships of those rating data is kind of interesting. So all the books are basically rated in a given week of 2013, in April or June. So this book is rated in that week and has only 4 ratings, no other thing. And if you check each book, they are just rated in a given week, not over a larger time period. And there are websites that offers money to people to go and rate books on a weekly basis, and to, of course, hide it from being like a casual spam reviewers. Those users go and rate the books in different times. So temporal burst is one of the kind of indicators of the spam reviewers. But in this case, we were able to spot some kind of a spam reviewer activity by just looking at the connectivity structure, ignoring the ratings and the temporal relationships. And our other example was on the older paper relationships. I think it's very popular thanks to the VLP data in computer science. So what I did is just take the top database conferences, like Sigmod, VLDB, ICD type of conferences, and I tried to find the subgraphs of a person called Philip Yu. So he's a prolific researcher, professor at UIC, I guess. And previously, he was working at IBM Streams Group at TJ Watson. And I was basically able to find 2 kind of branches where his subgraphs are forming. In one case, he was appearing in a subgraph with Kunlun, and who is the current manager of IBM Streams team. And there's another subgraph which contains those 2. Burak is the product manager of that team, and the other people in that line are either the other researchers in IBM Streams Group, or this is the PhD advisor of Burak. And the nature of the subjects they work on are more related on the stream processing and InfoSphere streams product they work on. But there's another branch where we find Philip Yu and Charles Agarwal in the same subgraph, and there are more people again working at IBM Streams Group, but the nature of the topics they work on is kind of different than the bottom branch. They are working on more like the theoretical stuff, In particular, this was more graph mining kind of stuff, and this and these subgraphs are more on the theoretical topics, which has nothing to do with the product of the IBM strings. And those two subgraphs are basically merging, having a common parent, which are like more than 150 people, all working have worked at IBM string groups or did some internship at some time in the past. So those are basically anecdotal examples, and the ones that I show you are the ones that ring decomposition was able to find, which cannot be found by the state-of-the-art methods. Well, of course, it doesn't mean that ring decomposition is like definitely better than the state-of-the-art. There were some others where ring decomposition cannot find, and one of the things that I noticed in our approach was our algorithm was always inclined to find like two people having so many connections, common connections, and the one feature where we consider is how can we elevate that? How can we find like a larger kind of subgraphs in the leaf level rather than just two people publishing out a paper together? And one part of the problem is most of the metrics and the similarity definitions we use currently are defined for Bipartite graphs, but there is no enough literature on the Bipartite side. So I believe more definitions and the further studies will also help us to find better metrics and the similarity measures for the Bipartite and subgraphs.
So sorry, before you move on, so one of the things that network scientists are very interested in is for example, distributions of k-core. So for example, the relationship between like a core number and degree, or what is the distribution of core numbers if I have a graph that's Erdem, if I have a graph that's like block 2 level Erdem, if I have a graph that's Hierarchical, so on and so forth. So here, did you guys look at, for example, the tip values for nodes or the wing values for edges? What are those distributions? How do they vary across different graph models? Are the distributions you find in these real world networks match, for example, the block 2 level Erdem has a bipartite graph that they generate? Like, did you do any of that so we can have
So I have one
sense
student working on the exact thing that you mentioned regarding degree distributions of the core and degree. So most of the time what we see is once you drop like degree distribution, it is heavy tail, like you have few vertices with high degrees and many vertices with low degrees. In the core number decomposition, what happens is the range is way smaller. So most of the time the largest core number we see are in the orders of maybe less than 100 in a million edges per graph, and it decreases for a while. But the largest core number is basically indicates the leaf in our nested hierarchy, and most of the time you find like a jump there, which is basically corresponding to the densest subgraph, where there are like 100 vertices having the core number of 20.
So I have a good sense of the relationship between core numbers and degrees. So for example, core numbers and degrees usually agree when the node has low degree, so on and so forth.
Yeah.
But I don't have any intuition in terms of like tip numbers or wing numbers, or if an edge has a truss number. Like, so any of those that you've looked at?
One thing we checked was the butterfly distribution for the node and edges. Again, we observed some kind of a heavy tail kind of distribution. And one difference that I remember regarding tip and wing than the core decomposition is we got like the largest wing number of a tip number was kind of high, larger than the largest core number you can think of. So it was not like less than 100, but it was in the order of 5,000 or so. So, and we were basically observing some jumps. In the K-core, most of the time you observe a range of vertices for different core values, but consecutively. In tip and wing cases, we see some jumps, and those are basically due to the definitions. So we are.
I see. So could you go back to the previous slide just for okay? So what you're saying is that for a particular vertex, right, I could have a tip number the same way in a bipartite graph. For a particular vertex, I have a tip number, which is analogous to in a unipartite graph, I have a core number, right? And are you saying that the distribution, like I know what the distribution of a core number is in a unipartite graph, is a distribution of a tip number in a bipartite graph similar to the core number, or no? You're saying there was some jumps?
It is a little bit different. I mean, the core number you usually have like a limited range, the maximum core number. But in the tip case, this goes a little further. But it is not as skewed as the butterfly distribution or the degree distribution.
I see.
And regarding the random network approach, one of my guys are working on that, and that is definitely an important thing. I mean, I find especially that bipartite graph very interesting, and they somehow overlooked in the literature, but there are, I think, too much work to do in this space.
Okay.
So the last thing I will talk about is
you have like 14 minutes. Just so you know.
Okay. Yeah. So the thing is, in the peeling algorithm, we always talk about finding the minimum degree vertex, minimum edge vertex in the entire graph. So you need to have like a global view of what's going on in your graph. And every time you should be able to answer where is the vertex at the minimum degree. So this basically requires you to watch the entire graph. And this is an inherently sequential thing actually. So this is like the pseudocode, and this for each unprocessed archaic with minimum DS, you need to either keep a heap or bucket data structure, and this basically creates like iterative processing. It is inherently sequential, and the only parallelism is possible inside the loop. So if you have fine-grained parallelism rather than a coarse-grained, which is expected to give a better speed up. So there is no local computation. And the other thing is, there is no sense of approximation at all in the core number or the trust computations. The densest parts, the leaves, the bottom, are not revealed till the end. So how can you come up with some kind of approximation scheme where you can find those leaves like early in the algorithm? And that is also related to the iterative process. If you follow this scheme, you won't be able to get that till the end of the algorithm. So for this purpose, we basically started thinking, how can you find the core number of a vertex by just looking at immediate neighborhood? So it's basically a local computation kind of thing. And here I have a graph with the core numbers denoted on the vertices, and the questions we explored for a while is, if I just check this, is there anything that I can compute based on the labeled core numbers that I can function defined on those vertices? And thankfully there is. So finally the H-index computation is useful for something. So in this case, if you go and check the H-index of the neighbor core numbers, you find the core number of your own vertex. So in this case, it's 3, 4 times 2. In this case, 2, 2, 4 gives you the core number of 2. So for those who don't, sorry.
What is the H-index?
Yes. So H-index is historically defined for the citations that each paper receives. So if you have
H-index.
Sorry?
H-index? The average.
Yeah, H-index. Yes. In this case, it's basically the largest number H, such that each of those numbers are larger than H. So in this case, I have 3, 4, and I have 2 numbers larger than 2, and this is the largest number I can get, so it's 2. In this case, it is 2 because I have 2, 2, and I can't go to 3 because those are less than 3. So it is basically a linear time computation for a given set of numbers.
So how do you visualize this?
Yes, so to find the core numbers from the beginning, what we start from is the degrees. So the seed of information at each vertex is a degree, and starting from degree, if you repeat that H-index computation, all the vertices, it will converge to core numbers. And it is actually first introduced by Liu et al. In some physics journals, I don't remember the name. But the thing is, degrees will converge to core numbers, and there are some convergence proofs for that. And the thing we observed here is, since we have a general framework for nucleus decomposition that unifies the k-truss and the other decompositions, you can generalize this for the trusses or higher orders. And the convergence bonds in the literature are basically talking about very kind of natural things, that the number of nodes is one bond that you can define very loosely. And what we introduced is the notion of degree levels. So it is different than the core numbers, but the idea is, for instance, if your graph has 10 vertices with core number of 2, you probably you didn't assign those 10 vertices the core number of 2 at the same time. You assign some of them, and then those new vertices basically got the degree of 2, and then you assign them. So it basically creates a finer grained structure than the core numbers, and we use that to prove like a better convergence bonds for core and truss conversions. And this is like the toy example that I show degrees on vertices, and what I do is just for each vertex I check the blue numbers around me and compute the H index. So for the first step, this changes. 1, 2 gives me 1. This changes as well, becomes 2. If I repeat the same thing, I see that this is changed, so it becomes 1 there. And at that point, if I do any computation, I won't see any update, so it means it converged. So here I basically do the computation with respect to the previous step. I use blue values to compute the red values. But of course, you can do better by using like the most up-to-date values, which correspond to asynchronous computation, and it will converge faster. And regarding the generalization, the main thing that we consider is, again, that bipartite representation. And the thing is, an S-click is as strong as its weakest I-click. So what I mean is, if you start from those values, 2, 3, 3, 1, those are triangle counts, then you go and find the collections of those, 2, 3, 3, 2, 3, 1 here, 3, 3, 1 here. And then for each vertex, you go ahead and compute the H indices of the values that are here, but the minimum values. So you got 2 from here and 1 from here, for instance. Similarly, you got 1, the value of 1 here to compute your H index. If you do that, again, your values, the intermediate values, will converge truss values after a while. And as I said, there are like 2 kinds of approaches, synchronous and asynchronous. K values can only decrease, and you can play with some heuristics to speed up those computations. And the best thing about those are local computations. You don't need any kind of a global computation, or you don't need to watch the vertex or edge to determine degree or triangle count in the process. So those are some results on real-world networks. One striking thing we observed is the convergence is actually happening in the first few iterations. So the candle tau difference between degrees and the core numbers, or the triangle counts and truss numbers, are basically getting very close to 1 in the first few iterations. Here I don't show the entire spectrum, but for most of those graphs, the real convergence number is in the order of 50 or less than 100. But in the first few iterations, 99% of your vertices will converge at it. So you don't need to go through the end, which is the nice thing for approximation.
What's the WN graph?
Web Notre Dame.
I see.
Yeah, this is Facebook, opinions, Twitter, Web Notre Dame, the Wikipedia edit relationships. And the other thing we checked was those leaves in the bottom, how quickly they converge, how quickly you can find those structures. And for that I find the F1 scores, and again, we see like a very sudden kind of jump in the first few iterations. We get very similar subgraphs to those leaves in the full computation of coarse and trusses. So one problem is, of course, you don't know when it's going to converge, right? You have no idea to know if that wiki network will converge in 100 steps or maybe 1,000 steps. And we have a good indicator to watch the amount of convergence during the computation, which is the ratio of active vertices in the core case. So you basically watch how many vertices are active in a given timestamp. So it is basically how many vertices are computing the action method of itself. So one of the optimizations that I didn't mention is you don't need to run this entire thing for all the vertices, but you can basically let them push some notifications among the vertices to wake them up for like computations that are expected out there. If I have changes in my neighbors, I update that vertex to make its computation. So that's what the active vertex corresponds to. And what we basically observe in different graphs is if you find that 40% of ratio in the active vertices, so here the accuracy is the dashed lines, so it's approach to 1, and the other lines are the ratio of active arc lengths, shown here. So if you go to like 40% of the ratio, you will have 90% of accuracy of the work.
So the bell graph that you showed, the bar, sorry, the graph that you showed as an example. So yeah, that one. So that kind of indicates that you need to traverse the entire path in order to converge, right? So it's extremely long.
Yeah.
Where the information to propagate, you would need to traverse.
Right. That is what the convergence process does actually. You don't explicitly traverse. For instance, we know that those two will have the core number of 1, but during our iterations, this one will first converge and then this one will converge.
Right. It's a lollipop graph.
Sorry?
I think it's called a lollipop graph.
Oh, okay.
But this kind of indicates that the convergence would depend on the expansion.
Yes, there is some information propagation necessarily going on from vertex F to vertex A here. So degree of vertex F is 1, and the vertex A will only know that in the third step.
So possibly these numbers that you gave will not be the same if the graph was something like that versus if the graph was an expander.
By expander, you mean the diameter is larger?
Well, that that the relaxation time is small, or that the ratio of the cuts. Wait, the definition of expansion, the ratio of the, like that. There are no two sets that are big but have a small cut.
Yeah.
Like that. That would slow up propagation. So here it is.
So I think that is more related to how the two converge. And one of the things we observed is having like a small diameter in most of the real world social and information network helps that.
Right.
But if you train it on a road network, which is expected to have a large diameter, we expect the information propagation from one end to the other end of the graph will take more.
Right.
So if you could wrap up. Please.
Yeah, I mentioned. And the 40% ratio gives 90% accuracy, and if you see the 10% active vertices, you will have 98% kind of accuracies. And as I said at the beginning, it is about approximation, so it enables you to explore different trade-offs between time and quality. So this is like the trade-off chart where we have different speed-ups with respect to the full computation if you let the accuracy to be 90% or 80%. So this is for the truss and this is for the 340 compositions, I guess. And regarding the speed-ups, I just did some shared memory implementation with OpenMP framework. And if you jump into from 4 to 24 threads, can give you like 4.8 or 4.7 times speed-ups for different compositions. And I expect better speed-ups can be obtained. For one of the problems with truss, there was a recent HPAC challenge organized by DARPA in the last 2 years. They have more fine-grained algorithms which can work concurrently with what we propose here. So, conclusion, I try to like an overview of what I did on the hierarchical dense subgraph discovery space. So this nucleus decomposition is useful to understand the relationships between different structures, vertices, edges, triangles, and so on and so forth. It is a wide application space and it's a challenging problem as well. There are so many opportunities for introducing like faster algorithms. And one of the things that I'm pretty excited is to explore the bipartite graph. So it's definitely more challenging and more things to do. So local algorithms are useful for the approximate computation and they're suitable for like vertex programming kind of things like trackable graph lab, distributed graph processing stuff. And we also have like an ongoing work on the providing this as a tool for network analysis. So instead of trees, we use some nested circle kind of visualization. Again, the densities are color-coded, but the nested hierarchical relationships are basically, if there are multiple circles, those are correspond to the kids of the subgraph that correspond. And I think that's it.
Excellent. Thank you. Perhaps one more question, if there's a question for her. I can ask. So one of the questions was, you were saying that in terms of the second part, there's no guarantees on convergence.
There is a guarantee on convergence, but we don't know when it's going to converge.
I see.
So there is like a loose upper bound on the number of vertices.
I see.
But yeah.
So what is that loose upper bound?
So the loose upper bound is for core decomposition, is the number of vertices, but we basically give a proof for a better upper bound based on those degree levels, which is the final grain core decomposition. So you can have multiple degree levels for the vertices that have same core number. So those are basically the ones that appear at once, the minimum degree ones at any time.
Great, thank you. Thank you again.